This is Mary Simo. I'm part of the XOS sales and marketing team, and on behalf of XOS, I'd like to welcome everyone and thank you for taking the time to join us. I have the pleasure of introducing today's keynote speaker, Patrick Wilgie. Patrick has been with XOS for nearly 7 years and is currently sales manager in the XOS Petroleum Analyzer Division. He is highly regarded by our customers and his colleagues for his expertise in technical engineering and his success in partnering with clients in the petroleum industry to deliver application-specific solutions to meet their elemental analysis needs. Today, Patrick will explain how changes in the market are increasing the prevalence of heavy metals in crude. He'll review the warning signs and the potential impacts on production, and he'll explain how high-definition XRF technology, referred to as HD XRF, can be used as an ICP alternative to deliver fast, precise, multi-element detection. And as Kara mentioned, at the end of the presentation, we'll open it up to questions. So with that, I'll hand it over to Patrick to get started.
Thanks, Mary. Hello to everybody who's out there. Again, we do appreciate you all calling in and listening to us today. I know some of you have already heard me talk about this once or twice, so we will go over some similar items, but maybe also you'll have a chance to learn some things. And then once we're done, we can go ahead and answer some questions for you, and we'll go from there. So anyways, just to get things started, like Mary said, I want to talk to you a little bit about our alternative for measuring metals in crude oil, an alternative from ICP, and also some other methodologies that we'll go over a little later on. And the instrument that we do that with is what we call the HD Maxine. So for those of you who may not know XOS as well as a company, I did just want to briefly touch on who we are and what we do here. So XOS was founded about 22 years ago. We're based out of the East Greenbush, New York area, so near the capital city of Albany, New York. And we started off pretty much making X-ray components and OEM pieces. But over the past 10 or 12 years, we've moved into some different markets. Some of you are well aware of that with our Cindy sulfur analyzer. And as you can see on this slide here, listed under our elemental analysis solutions, we have crude oil feedstocks, petroleum products, refinery process streams. So we do that with analyzers such as the Cindy, such as the Maxine, and others that you know about, like the Chlora. But we'll go into that in more detail a little later. Just to briefly touch on it, we also do have some analyzers that are more geared to the consumer products industry, and that's for heavy metals determination and things like jewelry, children's toys, paints, fabrics, ROS testing, that kind of stuff. So if you have any interest in that, feel free to contact us after this, and we can talk about that in more detail. But today we will focus more on the petroleum side of things. And then finally, as I had said before, the last part of our business is the X-ray optics and subsystems portion. This portion of our business is more niche business. We sell into some other manufacturers of X-ray equipment. So that just gives you a little brief overview of what XOS does. Again, if you have any questions about this, feel free to ask a little later on. This is just another slide that will show you basically the same thing. You can see here's our Cindy analyzer, and then we have a process analyzer, which we can also do for petroleum products. And then for consumer safety, as I had noted, we have analyzers for measuring toys. You can see that with the nice little wooden train down inside of here. And this is our HD mobile handheld product for quick, precise determination of heavy metals and more or less solids it comes to because, like I said, it's toys and jewelry and things like that. And then our X-ray subsystems. So this is what we would call an X-beam. And these down here are polycapillary optics. So to get right into it, I did want to talk with you all about the way the industry is kind of changing. And obviously, just from looking at the list of participants today, I think most of you are aware of what's going on. And this shouldn't be much of a shock to you, but we really need to go through it as a bridge to what we're going to discuss about the analyzer itself. Obviously, there's many new crude sources out there, shale oil, stuff coming from down in South America, things in the North Sea. And each of these crudes has their own specific issues, benefits, you name it. So these changing crude sources, sometimes they can be heavier, they can have more entrained contaminants, the way that they get them out of the ground can cause adding more problem elements to the sample itself, to the crude oil itself. And because of that, we're seeing different things like increased blending to meet contract specifications for different crude oils. If you look at the NYMEX spec for sweet crude, for WTI, it has specific things on there, but they're not all that specific because really at the end of the day, you're looking at things like BS&W, and sulfur levels and simple things like that. So what we're seeing and what we're hearing about in the industry is people blending these crudes, and by the time they get to the refinery level, you bought it as a nice sweet crude, but in effect, it's not exactly what you bought, right? And there are other problem things in that crude which can cause issues with your production and things like your desalting and your catalyst and the like. So. Just last week, I was or 2 weeks ago now, actually, I was at the Crude Oil Quality Association meeting, and they have been very, very proactive in getting added specifications to these contracts. And one of the things they've been working on, which I can talk about in more detail here, is adding a nickel and vanadium specification. And so that would be at 8 ppm and 15 ppm. To make sure that the crude that's being sold is under that level so that what ends up showing up at the refinery or in the pipeline is closer to what they would actually be expecting to get if they were buying a typical WTI. So currently the analysis of these types of metals are done by ICP, other variations of XRF, AA, atomic absorption, as you know. And like I said, I know that many of you are very familiar with this, but I did just want to go over it as a bridge to what we're going to speak about. So just to list some of the known offenders here, and these are particular things that we're good at measuring. So obviously I understand that there are many other elements I'm sure you're interested in, but these are the elements that this instrument is really honed to perform the best with, and we would think, as far as XRF goes, is one of the best instruments on the market for this stuff. So nickel, obviously, high levels can produce off-spec coke. It can deactivate your cracking catalyst, and it can cause emulsions. And actually, there's been a number of articles written about, the effects of nickel and zinc on these emulsions, which can lead back to poor desalting. Vanadium, high levels, again, can produce that off-spec coke and deactivate the cracking catalyst. And then some higher concentrations, it's been able to cause issues with corrosion near the desalter. So iron, similar things, including fouling. Now, iron's a little bit more of a different beast sometimes because it can show up in some different forms in the sample. But what we would do is we measure total iron, so we would just give you a total number. We wouldn't be speciating between, iron oxides or any other compounds that might be in there. And then, as I noted, zinc, along with nickel, can cause emulsions in high concentrations, which can lead to poor desalting, which I know we're all aware of. With poor desalting, you can end up with all kinds of issues, including higher salt content in the crude in the output of the desalter, and it could cause problems downstream with corrosion, if anything gets through. So, and then there's some other problem elements which we've heard about, which include chromium and calcium. Now, calcium, it doesn't seem like it's necessarily a worldwide problem. We are hearing more about calcium issues with things coming out of the North Sea and a few other locations. And if you have more questions about that, feel free to ask. I may not be the expert, but if I have to, I can get you the answer. So just to keep moving along here. So that kind of sets us up for what our issues are. There's problems with your changing crude slate. You're seeing crudes with different elements in them. And I just wanted to go over what XOS can do for you in that aspect. Along with the Maxine, as many of you know, and this is more of a sales pitch now, we're going to look at everything briefly. So we do have Cindy analyzers for sulfur, which, again, from looking at the list, I know many of you already own a Cindy unit and do some sulfur testing on finished products such as gasoline, diesel fuel, jet fuel, things like that. But we also do make a Cindy 2622 instrument, which kind of opens the spectrum of things you can measure. So you could do anything up to crude oil and in between, because 2622, as you know, is a ASTM method for general sulfur and petroleum by WDXRF. The OTG is a more portable version of that sulfur analyzer. And then we also have an online sulfur analyzer which can be made to work on finished product streams or crude oil streams. The signal analyzer, which does silicon in finished products and in crude. Phosphorus, which I know is a pretty hot issue at some refineries. I know I didn't touch on it on the last slide, but that's because it's not one of the elements we're made to do very well at low levels on the Maxine, but with a single phosphorus instrument, we can get down in the 1 ppm range with this Phoebe instrument. And so the Chlora, which I'm sure many of you are also aware of, is our chlorine instrument. And that's getting used right now in many applications in the industry for crude oils, using a water extraction to do organic versus inorganic. We can do catalyst measurements and fine powders. We can do aqueous measurements in your overhead waters or your sour waters. And we can also do that online. We can run a process stream right through it and give you a total chlorine number, and this is made to handle crude oil. So it would give you a good accurate measurement just as the benchtop would. And last but not least is our analyzer of the day, the HD Maxine, which I'm going to get into a little more detail here in a second. But first I do want to talk about the technology behind these analyzers, just so everybody is clear. I do get a number of questions about, what makes the Maxine different? Is it just like a Cindy? And the answer is mostly no, it's not like a Cindy, but there are parts of it that are very similar to the Cindy. So if you see here, you can see our traditional setup for an engine inside of one of our analyzers. And this is what we would call monochromatic wavelength dispersive XRF. And so with that, we can make analyzers that are very good at measuring low-level sulfur, chlorine, silicon, but they're only made for single element analysis. As you can see here, we have an X-ray tube, and that's a very low-powered tube, and it hits this first optic here, which monochromates and focuses the X-ray on the sample. And then using this second optic, we basically are just trying to collect that XRF and focus it into the detector. So using that second optic, we're limiting ourselves to just getting the sulfur K-alpha beam or just getting the chlorine K-alpha beam. And so what that does is it allows you to measure very low levels for these lighter elements that would traditionally be a little trickier, and then in some cases you would need a more higher powered instrument or a more complex piece of equipment. But the way we do it, it's all fixed, so everything's just sitting inside the engine fixed. And once we hit this detector, the signal to the noise ratio is very high, so there's very low background, and you're getting just this sulfur X-ray fluorescence. And so as I noted, you can use that in a benchtop, you can use it in the process, and like I said, for process analysis of high viscosity streams, we can do that as well using this MWD XRF technology. So when we switch over to what the Maxine uses, which is what we call HD XRF technology or high definition XRF, I know it's a fancy name, and I think we came out with it about the time when HD TVs were really in style for the first time. So it really is what it says. We're taking XRF, which is an industry standard, and we're really pushing our limits, using our optics to give you that high performance. And what happens here, and the main similarity between the MWD and the HD XRF are the optics. So the optics are of a similar ilk. So they're both doubly curved crystals, and so using those doubly curved crystals, you can imagine that we do get a similar effect as we would on the front end here of the MWD XRF. But in this case, what we're doing is we're using an X-ray tube, and we're using different optics and different powers to do different levels of excitation. And so using those different levels of excitation and a very high-powered detector as opposed to the detector on the MWD XRF, which is a very simple pulse counter. The detector on the HD XRF instrument is more of a silicon drift detector, and it's very complex, obviously, and it's made to handle many multiple channels in a very complex spectrum. So using this monochromating energy, we can stimulate different elements at different energies, such as chromium, iron, nickel, vanadium, but at the same time, we can also tighten those numbers up using different energy levels off the X-rays. So we can still see elements like sulfur and chlorine down in the 10 ppm kind of range, but we cannot get the same levels as we would with MWD-XRF. But this HD-XRF technology is really built for these wear metals in crude oil, these transition metals. For many of the elements, as you'll see, we have a sub 1 ppm detection limit, and for some of them, it's sub half a ppm. So very good. A lot of work went into designing this setup, and it's really unlike anything anybody else is doing. I know that I'm sure many of you have seen dual target systems and things like that, but this is really cutting edge. And right now, it's in our HD Maxine. And it's also in our consumer products line of instruments, which I showed you earlier, because obviously the main elements there are also metals like lead and cadmium and things like that. So that gives you a little bit of an idea of this. And just to further dig into it here, you can see on the right-hand side here some of the energy spectrums that you get from a typical scan with HD-XRF technology. You can see here some very well-defined peaks. I know they're very small letters to read on there, so I wouldn't waste my time taking out your glasses to look at them. But you can see the peaks are very well-defined, and using these peaks, we can give you very good repeatable numbers. Just to show you a little bit about how our monochromating works here, you can see that this energy spectrum is after it hits the doubly curved crystal optics. So you can see we've really focused it down into one energy level, a very small spectrum, and that's how we can get such good numbers with such low background. So this is the basic concept here. The tube, which is polychromatic, up into these optics again, and not all of these optics are all hit at the same time. They're all hit at different times. And then that monochromating excitation hits the sample, and this sample is pretty much right in the air because there's no vacuum, there's no helium purge. And once it hits that sample, the excitation that comes off of it goes to that silicon drift detector, which we talked about. And so really, what that buys you is a number of benefits. It can give you a multi-element analysis, unlike some of our other analyzers, which are made for just one element. Of course, that's mostly because of the lightness of that particular element. It can give you exceptional detection performance for some of these critical elements in crude, like your nickel, like your vanadium. You can get sub-ppm detection limits and in a 200-second run, which is very, very, it's impressive to me anyways. There's no purge gas or vacuum needed, as I noted. The sample is pretty much just sitting right above where the X-ray source is, and your detector is right there to catch the X-rays coming off of it. There are windows in place to make sure that there is no leakage down into the instrument, because as you can imagine, I know on some of those bigger WD-XRF systems, there are, if you get anything onto the X-ray tube, that's very bad. So we've set it up so it's not simple for that to happen, and I think that's really a benefit because I know there are concerns about that in the industry. There's really no sample preparation needed and no acid digestion, obviously, because it's not like ICP, it's XRF, right? So it's non-destructive in that sense. So for most samples, you would really just take a pipette and load them into the cup, and then once they're in the cup, you put them in the analyzer, you pick which mode you want to scan in, and then you go from there. And in 200 seconds or 600 seconds, you would get a very good result, and you could run repeats on it. It's very simple to use, and I'll show you the user interface here shortly. Low power X-ray tube. Much like our Cindy systems and our Cora systems, it's set up to run at a very low power. You just plug it right into a regular wall outlet. I think the tube is probably 50 to 75 watt. I'm not sure specifically what it is, but it's very, very low power, all things considered. And using our optics, it eliminates a lot of the scattering background. And as I noted, you have the ability to screen quickly with a 200 or 600 second measurement. If you just, want to know if there's way too much nickel in your sample, you can just run a quick measurement. Or if you want to really quantify and you're doing test work to make sure you can, specifically what's happening. You can run a 600-second scan, and over time you'll see statistically those numbers are probably tighter. So this list of elements up here is just a short list of things we can do. In a second here, I'll get into all of the elements we can do and at the levels. But for now, let's talk a little bit about the calibration of the instrument. I do get a lot of questions about this. I know on our current line of analyzers, it's very simple to calibrate, right? You take 6 samples, you run them, you get a straight line basically. Well, hopefully you get a straight line. But with the HD Maxine, we do things a little differently. But there is an addition to that, which I want to talk about briefly. So the main calibration function of the analyzer is fundamental parameters. And I know some of you are already aware of that, but I'll explain it briefly for some of those of you who aren't. What we do is we run a blank sample to set the baseline. We run a sample with known concentrations of elements to set the peaks and also to allow us to correct for some interferences. And then we run that sample one more time to impose the elements that are known onto the spectrum peaks with the background. And so once we do that, what we're doing is we're creating a model. And so then every time when you run a sample and you get a certain number of counts, you know that how many counts, in which peak, what element that is. So it's very complex as compared to linear calibration, which leads me into the next part of this, which is many users have asked us for an ability to modify this model without going back and just using the same set of standards. So something that you can't necessarily see here, but I know down the road we will be making a video to show everybody, is that we'll have an empirical enhancement. And so that sounds kind of goofy, but the basic idea of it is that if you wanted to get tighter numbers for, say, something like sulfur, then you could run a number of known standards of just sulfur, and using that it could tighten up your model for the sulfur peak, which actually we've found to be very beneficial to some customers who, they get good numbers, but they want, they just want it to be tighter and tighter. And as the limits go lower, you want to get the best number possible. But as I said, we will have more information on that in the future once I'll get a video up online with the help of Mary here, and we'll all be able to see how that's done. But the basic concept is that in order to tighten that up, we would run known standards of known concentrations of certain elements to tighten that up. So from there, I do want to show you just the basic operation screen of the analyzer. So there's a lot more to this, but I didn't think it was a good idea to spend half of our time just walking through screenshots. But here you can see the basic measurement screen. And this is, there's a number of different elements on here if you're used to working with our Cindy analyzer that aren't typically on there, and I think some of them are very much to your benefit. You can see here, you can pick a matrix. And so what will happen is we'll set the analyzer up before it goes out with some different matrices. We'll set it up with an oil matrix, a powder matrix, and a water matrix. And each of those matrices will be adequate. With oil, you'll be able to run pretty much any, a crude oil, a heavy oil, anything like that on the oil curve, because statistically the differences between those matrices are very small, almost non-existent in some cases. With a water matrix, it's necessary, obviously, because of the oxygen content. So with XRF, there is an oxygen interference which can be taken care of typically with calibrating for it, but in this case we can actually make the model automatically adjust itself to running an aqueous sample. So if you wanted to run water samples, for heavy metals or anything else, you would just select here in the matrix, and then it would know to switch that model for that. And then obviously the powder one would be for other things like catalysts and cokes and anything else you would try and throw at it. The next thing of interest here is the optimization. And again, down the road when we make a video, I'll be able to go through all this with you guys and just show you in a nice tight package. But what happens here is that you can select how to optimize the instrument. So the instrument, because it has different optics that can be run at different energy levels, what we can do is we can optimize it, say, to just run the heavy metals with a longer time. So if you wanted to, measure and down closer to the ppb levels, very low for something like nickel, you would select what we call a high Z scan. Or if you wanted to get better resolution on something like sulfur or chlorine, you would select what we call a low Z scan, which obviously is lower on the elemental table, on the periodic table. You can see it does give you the option here to put a name in for the sample, a lot number in, and then you can put your operator name in here, and you can put a description in here. So I would recommend that if it does come to putting a full description in, that you can hook a keyboard into the instrument and type that out. Otherwise, there is a pop-up keyboard that will come up on the screen that you can type in with manually that way too. You can select the number of measurements, so you can run repeats just like you would on a Cindy unit. And then here, this is what we call our standard. And so once I go to the next screen here, I'll show you where that's going to benefit us. But you can set up different standards. So if you had different samples, right, so if you had a crude oil that you wanted to check for X, Y, and Z at these levels, and if it's bad, you want it to come up, red, you can do that. And once you hit your quantify button and you wait 600 seconds or 200 seconds, what will come up is this screen. So this is your summary screen. And this can actually be formatted to put whatever elements you would have of interest up here. Right now there's a couple of strange ones on here. I'm not really sure why they're there, but so you can set this up to just list out, nickel, vanadium, iron, zinc, and whatever else, and just pick 8 to 10 elements you want on this home screen. And from here, you'll get your result with a ppm value, which you can either choose to print it out, or you'll have a file of it, which you are able to save to a USB stick, or even potentially transfer across a network. Is something we've been working on, so the LIMS system could just pick it up. So here, you can look at your full results page as well. I actually don't have that screenshot here. I apologize, but so this is your two basic screens though. So your measure screen, which we just looked at, and then your results screen, which is what would pop up and what your operator would look at. And we can set these squares up to come up in different colors. So if you want your operator to know that it's bad, we can set it up to come up red or yellow if it's on the fringe of what it should be. You can set the ppm constraints up that way. So. It is a little different from our traditional analyzers, but we feel that the user interface is actually an improvement in some aspects, and it will give you guys a little more flexibility. So as I promised before, I told you guys I would pull up a table of elements here with our different limits of detection. You can see, as I noted, where you get the best results are with your metals. You're looking in here, vanadium, chromium, iron, nickel, and then also with some of these even things like lead and mercury, we're almost in the ppb range. And I know I've gone over these numbers with a number of you, but I figured it would just be good to pull it up so you guys could see it. And we will be supplying this after the fact, so you will have access to it. Calcium, potassium, down around the 1 ppm area. But then you see here too, just to point it out, as I noted, we do get a lot of questions about this. Silicon, phosphorus, sulfur, and chlorine. They're good numbers, and for something like crude oil, you can probably get away with something like 9 ppm for a limited detection for sulfur, because most of your crude oil is going to be higher. But if you still wanted to measure finished product, we would recommend going with one of our single element analyzers like the Cindy, or for chloride, something like the Chlora. But again, I'll give you guys a second to look at this, and then I'm sure there'll be more questions after the fact. I know some elements that'll come up after the fact will be things like sodium, which unfortunately is so light that we can't do it effectively with the HD Maxine. We could do it in high concentrations with a single element instrument, possibly, but for this, it just doesn't work. And then aluminum, it's just too light for the instrument to see in the format we've set it up with. So again, these are 10-minute measurement times with hydrocarbon matrix. If these get updated in the future, we'll supply you with that too. But for now, this is where we're at for limits of detection with the Maxine lab model. So. And then I wanted to go over just a little bit of data with you guys. So typically, when you read a white paper or an app note, somebody runs a known standard and they get some good results on it, and I figured I'd just show you all that too. I mean, obviously, when you're running a known check sample, it's a little easier. But it is a testament to the performance. Now, this is down at 5 ppm. For these elements, most of the limits of detection are below that. So even a 1 ppm standard would probably still yield pretty good results, if not the same. You can see your standard deviations here: 0.14, 0.09, 0.05, 0.08. I mean, that's really fractions. And very, very tight numbers. So the instrument is very repeatable. And, with a known check standard, obviously, I think the numbers are going to look a lot better than they would, with any other sample, but they look good here. So, and that's why I also included some repeats here on some crude oils that we ran. You can see I jumped around a little bit with the detection times. I just wanted to see what kind of response we would get. If the number went way out of balance, if I switched it to 200 seconds. And you can see here that the numbers stay pretty tight. We're running things like Mexican blends, Saharan blends. So they're very different crudes coming from different parts of the world. And for things like nickel and vanadium, the numbers were very good and they were very repeatable. So you wouldn't need to worry if you needed to run a quick scan and just get a 200-second run and get your results from that. So just thought I'd point that out. So we didn't just look at a mineral oil standard, and I told you how great they looked there. So, so I just wanted to go over a little bit about the differences between us and other XRF technology. This chart's a little wordy, so I'll just go over the basics. With standard ED-XRF, at the end of the day, it's probably a good low-cost instrument, but for performance-wise, it really just won't meet the needs, I think, of today's market. For some of these higher Z elements, as it notes on there, so your heavier metals, it just can't get down to the low levels that you guys probably need for your day-to-day. And then even some of these high-performance ED-XRF systems, we're seeing that they use these secondary targets, which can reduce the sensitivity by the time it gets to the sample, so you're losing counts. Some of them use purge gases. Some of the limits, they can do a little better than us on some of the things like silicon and the like. But for the elements we're talking about here, for nickel, vanadium, and nickel, vanadium, iron, the HD XRF technology is better. It just gives you a more tight result. And, both of those two are very compact systems too, I will note, the ED-XRF and the high-performance ED-XRF. So they come in basically the same package size as we do. So, if you were comparing those to us, that's kind of where you're at. And then with WD-XRF, so here we're talking about your big systems, your Panalyticals, your Bruckers. The low Z elements, again, they're probably better than us at some of these lighter elements like sulfur and silicon. But for things like nickel and vanadium, we really shine in that area. And so then we come in a small footprint. We don't use any gases. We don't use any special power. We just plug right into the wall and you run it for 200 or 600 seconds and you go from there. So I won't get too far into this because we could probably spend half the day debating different XRF techniques, and I'm sure everybody would be very excited for that. So just to recap some of the typical applications here, we did spend most of our time talking about metals in crude oil, so we can pretty much breeze over that. But we also have done some work for organometallics added to enhanced lube oils, different additive packages for different groups. Of particular interest here is, phosphorus and zinc and calcium, and being able to check what additive package is what and how much, they can charge for it, what benefit it'll give to that application. And so as opposed to using a big WD-XRF system or using an ICP, this could be a very fast scanning technique for these higher levels of things like phosphorus and calcium and zinc. So. And also for the wear metals in those lube oils, in the used lube oils, potassium, vanadium, zinc, very much kind of almost a similar application in some cases with some of the elements to the crude oil one. but also something we can do fairly well for most of the elements of interest, not all of them. And looking forward a little bit about the Maxine, I did want to talk about a few things. So at the ASTM level, as far as standardization goes, we do hope to submit data soon. I was hoping this December, but it all depends on how things shake out. But we'd like to initiate at least a method for nickel, vanadium, and sulfur in crude oil using our technology. Currently, we don't fit under any of the existing methodologies with the way we do things. So we've looked into that, but it looks like the way we're going to have to go is to adopt our own methodology. So that should really be kicked off late this year and into early 2014. And then also in early 2014, we plan to have a multi-element online analyzer available for process analysis. So at the refinery level, managing your crudes as they're coming in and checking them for these elements, so if there is a spike, you don't miss it because you're only testing every 4 hours, so you can keep an eye on it. At the pipeline level, at these blending areas, to make sure that they're blending correctly, and then so that it would be able to measure simultaneously for something like iron and nickel and sulfur at the same time, and that way, when it comes to buying and selling and trading these crudes, it would be much more transparent as to what was in there, and it wasn't just a sample taken once, 24 hours ago. It'd be continuously updated, so you really know what you're getting. And then finally, going into December, the end of this year, we hope to have the AccuFlow add-on available, which will help to reduce some settling effects in certain crudes. And so this is already available for our chlorine analyzer, because we have seen some issues when measuring straight crude oil with settling out of chlorides with the way that they're present in the sample. And I did just want to speak about that briefly here before we wrap up. It's what we call our AccuFlow technology. You can see here it's designed to eliminate the settling of particulates in crudes. These aren't every crude, because not every crude is made equally, as you all know. So it's really for specific problem crudes where you see these settling effects. And I can show you guys just a little bit of background and some data, right? So chlorides present to salts in crude. Salts are generally not stable in the crude, and they start to settle out over time. And so as you're running something and you run it for 300 or 600 seconds, it's going to start to settle out at the bottom, which gives you an artificial number. Now I know a number of my customers have gotten around this different ways, shaking samples, running shorter measurement times, all kinds of different things. But we were kind of looking for a more final solution to it, just so it's easy on everybody next time. So you can see here just a little data. This is watching a sample creep up over time. You can see that it starts way down here in the, I'm guessing that's somewhere around 40, 50 range, and over the span of an hour, it's crept up to 1,600 ppm. At 10 minutes, we're talking about 700. So you can see that there's a visible statistical issue if you just leave a sample in there and you just run it for 300 or 600 seconds. So you can see here, this is it measured statically. So that's putting the sample in our Chlora analyzer. And again, I'm using the Chlora as the default because right now, my data is somewhat limited for the Maxine with the AccuFlow, but the principle is virtually identical. So you can see here down in the 35 range, and it creeps up. With this flow-through cell, we get a nice consistent measurement. What's happening there, right, is much like our online instrument, we're able to keep the sample continuously flowing. And so by keeping it continuously flowing with warts and all the particulate, all the sediment, everything that's in there, we get a true accurate number over a 180-second measurement time rather than watching it settle out and jumping up to 400 ppm and everybody saying, oh my God, there's 400 ppm in there. It's probably actually 35. So you can kind of see it a little bit there. It's visualized a little bit here too in a similar way. The creep up and then the stable measurement with the flow through. So I know data isn't very exciting to look at. I'll show you what the setup is here. So what we do is you can see this is the orange cover to the Maxine or the Chlora or what have you. And what we do is we put a drive motor in here and we drive that sample down through a sample cylinder. As it passes by the measurement window, we're hitting it with X-rays. And while we're hitting it with X-rays, we're counting. And so over that 180-second measurement, things are continuously flowing, outputting to a drain tube and into a disposal jar. And we get very good data by doing this with these problem crudes. And so it's just something I wanted to talk about a little bit, and then kind of tie it back to the Maxine by saying, it will be available for the Maxine in December. And if if we run samples for you, and you send them in here, or we do it in the field at a demo and we determine them to be more problematic, maybe we need to talk about this as an add-on. So. And that brings me to the next slide. So we can do demonstrations for you, either live in person or on the web. So if anybody wants to do an online demonstration, feel free to contact me or submit something to our website. Or if you want to set up an in-person demo, I can set something up with one of our local folks, or I'll come up myself for you. So whatever you need, if you have any questions, feel free to submit them through these channels as well. And then I guess I just wanted to say thank you to everybody for being here. And I know some of you had some questions, so I will get to those in a second. But here's all my contact info and a great picture of me. And so right now I can go ahead and take some questions from some folks, if that's all right. So I do have one question here. That says, what is the matrix for the detection limits shown in the slides? And so the main one, and especially in that big periodic table slide, is hydrocarbons. So if you would like a aqueous, which leads into the next question from the same gentleman. So if you would like an aqueous detection limit table, I would be more than happy to pass that on, and I can actually do that after the fact here. The next question is, are there any applications in environmental for water samples? And the answer is yes, and I will get you the detection limits on that. I've seen people look at any number of elements in water. Most recently, I know selenium has come up a little bit. So that is something we have seen. And then what else do we have for questions? We do have a question about what kind of standards are used. I did just want to, for calibration. And so I get this question a lot, actually, about the calibration. And so we do use an oil calibration matrix, and we use one that has known values of, I believe it's nickel, vanadium, sulfur, and iron, I believe are the 4 elements that are in it. And that's just what you use to map out the energy levels with the known concentrations. So that's how that kind of works. And then also here there's a question about the AccuFlow, with what kind of viscosity it can handle for sample flowing through it. And right now it's about 2,000 centistoke. So it can handle some highly viscous samples, but obviously not everything. And you could run into some things that were even higher than that. So I just are there any other questions? Feel free to submit them. There's only we have a few, so if anybody's got anything else, feel free, or if you want to contact me after this, I'd be more than happy to help you out. Again, the presentation and everything else will be available online, or we'll be able to send it to you after the fact. And if there's any questions on that, again, feel free to let us know. So.
Okay, this is Mary Simo again. Thank you, Patrick. And just to reiterate, we will be sending everyone who participated today a copy of this presentation along with the recording, so you should receive that in a couple of days. And again, Patrick's contact information is in that, so if you have any follow-up questions or need any additional information based on today's talk, just let us know and we'll get that to you right away. Thank you again for participating, and look for future information from us on other upcoming webinars on different topics. Thank you. Have a good day.